Okay, so mass, weight, and density. Let's do this one. So we're going to go over the notes first and then do a few past paper questions. Okay, mass, it's the amount of matter or number of particles contained in an object, and it's a scalar quantity because it doesn't have a direction, and the unit for mass is kilograms. We can also think of it as the measure of inertia. And what's inertia? It's the reluctance of a body to change its current state. We also looked at it when we were talking about Newton's first law of motion. So the more massive something is, the more inertia it has. Okay? You can think of like day-to-day examples as well. When you're pushing a loaded cart, it's heavier and it's harder to push it because the heavier mass is providing more reluctance, it has more inertia. So the more massive something is, the more number of particles it contains and the more reluctance it provides. Okay, next. Weight is the force of gravity on an object with mass m. Okay, so we have this formula W equals mg, and it's a vector quantity. The direction of weight is always towards the center of the planet or the attracting body, and every mass has this attraction or this attractive force. The larger the mass, the more force it applies on another mass to attract it towards itself. Now, when we're talking about planets, you will notice that there is this dotted line drawn around them. It's representing the region where this attractive force is going to act. So if this little m is outside of the circle, let me try to demonstrate it. So if this little m is outside the circle, nothing is going to happen. So let's say that this little m is an asteroid, okay, or a comet or whatever, and it's going past planet Earth. If it's outside of this region, it's going to continue its trajectory however it would like. But if it interacts with this circle, then it's going to be attracted towards the planet because it's entered the gravitational field of the planet. Okay, so you can think of gravitational field as the region around a planet where its gravitational force is going to act upon this mass. And the larger the mass, the higher the acceleration of the mass towards the bigger mass. And next we have the comparison between mass and weight. Mass is constant everywhere because it's the number of particles, and that doesn't change no matter where you are. However, weight changes according to location because it depends on the acceleration of free fall, or g, that we just discussed, which is changing here, right here, compared to this bigger mass. So the moon has a smaller gravitational field strength compared to the planet Earth. So your mass will be the same on both of these bodies, but the weight will be smaller on the moon compared to Earth. Okay. We use a balance to measure. Oops. Okay. So we use a scale, a digital scale, to measure mass, and we use a force meter to measure weight. Remember the instruments, please. Okay, lastly we have density. Density is just the amount of mass that is distributed upon a unit volume. So if you divide the mass by volume, you'll get the density of an object. And it's, here. So mass per unit volume of a material. And now we're going to look at the relationship of density with mass and density with volume. Remember that when you're looking at a relationship between two quantities, the third one has to be constant to ensure that your comparison is fair. Okay, so if you're looking at the relationship between density, relationship of density with mass, you have to ensure that you keep the volume of the object same. And what's volume? It's just the amount of space occupied by an object. So if we draw two boxes to represent the same volume, the boxes are the same size, so it's representing same volume. And you draw more number of dots in the first box to represent a higher mass compared to the second one, we can find out the volume of each of these boxes and compare them in the end. I drew a few dots here in the first box and called it M2. Actually, this is the second box, M2, and this is M1. M1 obviously has more mass than M2, and the volume for both of them is the same. If you divide this mass by this volume, you'll get 4. But if you divide the other mass with the volume, you'll get 2. So you see a very obvious relationship here that as the number of particles increased, the volume increased. Sorry, the density increased. That tells us that mass and density have a direct relationship. That just means if you increase the mass of the object, its density is going to increase provided volume is the same. Then, if you look at the relationship between density and volume, and in this case we have to keep the mass constant, you'll see that there is an inverse relationship between density and volume. And these are our results. I'm sorry, I'm not going to be able to go into much detail. For that, I'll come some other time. For now, I think we just should go over the important formulas so you can do questions. That's the main goal for now because your exams are around the corner. And afterwards, if we get a chance, we'll go over some derivations as well. Okay, now you should know these 4 formulas or 5 formulas at least. And it's just the formula for volume of a shape. And how the question will appear is that you'll be given the mass of the object and you'll be given important information that will help you find the volume. And firstly, you find the volume and then you plug it into your density formula to find the density of the material. And you'll only be able to find the volume if you know the formulas for those shapes. If you have a regular shape, then you will use these formulas. For irregular shapes, we're going to go over another method just in a few minutes. So your first shape is a sphere. It's 3D circle in simple words. And the formula is for over 3 pi r cubed. For a cube, you have L cubed. For a cuboid, you have just L into length into width into height. For a cylinder, you have pi r squared L. And for a prism, you just have the base area of the shape multiplied by the height. And the base can be a triangle, it can be um, it can be any shape practically. It can be a triangle, a rectangle, or a pentagon. Whatever your base is, you find its area and you multiply it with the height of that pyramid, or prism, sorry, not pyramid. Okay. Now, if you have an irregular shape, you cannot use a formula to find its volume. Instead, you're going to use the displacement method. So what you do is you take a test tube, you fill it up to a certain amount of volume, you measure the volume, that's going to be your initial reading. Then you put your irregular shaped object into the test tube. That's going to cause the water level to rise. And then you record the final volume. You subtract the initial from the final, and that will give you the change in volume. It's just the space occupied by that irregular object that you dropped in the test tube. So once you find the volume of your shape, sorry, not shape, object, you'll plug it in the density formula and find the density of the irregularly shaped object. Okay, let me see if there's anything else. Okay, so lastly, we have this idea of floating, like why do some things float and others don't? I think in the last lecture we learned something related to the pressure difference, but today we're going to look at the same floating concept in terms of density of an object. So if the density of your object is more than the density of the fluid, which is water in this case, then the object is going to sink, okay? But if the density of your object is less than the density of water, it will float. Okay, so we had this example as well, that a boat, like a metal boat or a cruise ship or whatever, it's very heavy, so why does it float and not sink? On the other hand, if you dropped just a small metal ball into the water, it will sink. So why does a heavy metal boat not sink, but a small metal ball sink? The reason is that the density of the metal boat is much smaller than the density of the water. But the metal ball has a higher density than that of the liquid, so it sinks. And we can prove it by looking at the formula and plugging in some numbers. You will be given the mass of the cruise ship, you'll be given the volume, and once you divide those numbers, you'll see a number for the density of the cruise ship that is much smaller than that of water. So it all comes down to density in the end, and there is a lot of empty space in the ship, right? So when you have a bigger denominator, it's going to give you a smaller answer in the end for your fraction. Okay, let me see if there's anything else. Yeah, let's look. I don't think we looked at this one yet. So let's look at the difference, not the difference, but these two things. Acceleration of free fall and gravitational field strength. So acceleration of free fall, it describes how quickly an object's velocity changes when falling freely under gravity. And it's this little a in F equals ma, okay? And gravitational field strength is the, sorry, wait, let me go back to the other page. Yeah, okay, so it's the same thing. Yeah, so gravitational field strength tells you, it's literally what it says. It's the strength of your gravitational field. So it's the amount of force that is applied on a mass in that field. So it's the force applied per unit mass. And it happens to be equal to acceleration of free fall. That is why oftentimes we're taking the value of acceleration to be that of gravitational field strength, g. All right, now let's move on and do some practice problems. Let me see how much time we have. Wait, where did my timer go? Okay, we do have about 15 minutes, so we should be able to do at least 5 problems. Let me see. Okay, all right, so the first problem, wait. Okay, so the first problem says a brick is placed on a Newton meter and then on a beam balance. What's measured by each instrument? We just saw it. This Newton meter is going to measure the weight, and the balance measures the mass of the object. So our answer is C. Which property of a body resists change from a state of rest or motion? We saw it in the notes just now. It's mass. It's the measure of inertia. It measures how much reluctance is a body going to provide if you try to move it. The higher the mass of an object, the more reluctance it provides, so the higher the inertia. Next, the mass of a stone is found on Earth using a pan balance. The weight of the stone is found using a Newton meter. Are the readings the same or different on the moon? What do you guys think? So the readings on the pan balance are going to be same, yes. That's because it's measuring the mass, and we learned that mass is the number of particles or amount of matter in a body, and the number of particles doesn't change, right? No matter where you are, it's always going to be the same. So the reading on the pan balance is the same, but the reading on the Newton meter is going to be different because it's measuring weight, and we know that weight is a product of mass and gravitational field strength. As the value of g changes, your weight also changes. The table shows weights and masses of 4 objects on different planets. On which planet is gravitational field strength the largest? So you have weight and mass given. Okay, let's write the formula that connects these two things. We have W equals mg, okay? And we want to know the gravitational field strength of each of these parts, okay? So you're going to rearrange this formula. G will be, this m here is being multiplied with g, so when you take it to the other side, it will be divided. You have g is equal w by m, and you can find g for all of these parts. Let's do it for part A. G of A is weight of A over ma, and that's just 2 by 20, and that's 1 over 10. Let's do part B. It's going to be 4 over 30, and let's do part C. It's going to be 6 by 40, and part D is going to be 8 by 50. You'll find all of these, and I think the number that you'll get is this one. Okay, it's going to be the smallest, but please compute these numbers and double check as well. I'm just doing this for now. Okay, the mass and volume of 4 different objects are plotted as shown. Which object has the smallest density? Again, for these type of questions, try to go back to the formula, okay? So density is mass by volume, okay? So let's do for A. For A, the mass is 20 grams, and volume, so mass is 20, and volume is 5. So 20 by 5 is just 4. For B, you have mass is 20, but the volume is 10, so that is just 2. For part C, we have, sorry, let me just get rid of this clutter. Yes, so for part C, mass is 10, and your volume is 5, that's just 2. And for part D, we have mass of 10 and volume of 10, so that is equal to 1. So the smallest density is part D. You can, wait, yes, it is part D. So you can either compute these numbers, or another way is by the relationships that we learned. We learned that density is proportional to mass, and it's inversely proportional to volume. So for smallest density, you would need the smallest mass and the highest volume, right? So you would need the smallest mass, which is 10, and the highest volume, which is 10, and that is part D. So you can either do this by computation, or you can just look at the relationships that we learned. Okay. Which statement about mass is correct? Mass is density divided by volume. We can go back to our formula and check. This is our original formula for density. And if we rearrange this for mass, we'll get density times volume. So no, mass is not density divided by volume. It's the product of density and volume. Mass is the amount of space occupied by a body? No, that's volume. Volume is the amount of space occupied by a body. Mass is weight multiplied by gravitational field strength. Let's see. So here we have mass and gravitational field strength involved. So let's look at a formula that connects those two. That is W equals mg. If you rearrange this for mass, you'll get weight divided by gravitational field strength. So that is also wrong. Mass resists change in motion. That is correct. We did it. That mass is the measure of inertia, or the measure of reluctance that a body provides to motion. So yes, mass resists change in motion. A student produces some revision notes on gravity, mass, and weight. Which statement is not correct? A gravitational field strength is a region in which a mass experiences a gravitational force. This is correct. We saw a diagram as well that was planet Earth, which we were considering to be the big mass, and our asteroid or comet was the smaller mass. And we said if this little mass comes within this region, the dotted region that I'm drawing here, if it comes within this region, then it's encountering the gravitational field strength of the Earth because it entered the gravitational field of the Earth, okay? So gravitational field is a region in which a mass experiences a gravitational force. This is correct. Gravitational field strength has units of newtons per kilograms. Let's see. W equals mg. We want to isolate g, so we'll take m to the other side. We have W by m equals g. Weight is a form of force, and the unit for force is newtons, and mass is kilograms. So newtons per kilograms is a correct unit for g. So this is also correct. Mass is a measure of the amount of matter, also correct. Mass is equal to weight multiplied by gravitational field strength. That is wrong. Part D is the right option. Two cylinders P and Q are made of copper. The height of P is twice the height of Q. Diameter of P is half the diameter of Q. Which statement is correct? So for these type of questions, please do not be fooled by this X's information. It's just to confuse you. Remember that density depends on the type of material. Okay, for the same type of material, the density is same. Okay, so it's equal for both of them. However, if you had two objects of different materials, then you'll need to use this information to find out the right answer. And I think we'll get a question. Let me see if there is one here. Okay, so I don't see a question on this yet, but we'll go over our past papers once again, and I'll teach you how to do that. So basically, the idea, let me give you a little bit of like a little summary here. So if you have different materials, remember this is the key word, different materials. What you're going to do is use this information. So it's saying that height is twice the height of Q. So your density is mass over volume, right? They haven't said anything about mass, so we'll assume that it's the same for both of them. Assume same. And we know that the relationship of density is inverse with volume. So what you're going to do is find the volume of both of these shapes, and whichever has a higher volume has a smaller density. Okay, we can try to do it. So this shape is a cylinder, and we know that, let's do volume of P is the base area, which base is just a circle, pi r L. We can call this L. Okay, pi r L. So basically, let me write that down here. Volume is pi r L. Okay, so volume of P is pi, and the height of P is twice the height of Q. So if Q has a height of L, then P is 2L. Okay, so if the height of Q is L, height of P is going to be 2L because it's twice that of Q. The diameter of P is half the diameter of Q. So that means if this radius is R, then this is going to be 2R. Okay? So for volume of P, we can write pi R 2L. And for volume of Q, we can write, let me see, pi 2RL. Okay? So that is just going to be 2 pi RL, and that is equal to 2 pi RL. So you see, in the end, we got the same volume for both of them. Same volume, same mass means same density. But we won't do all of this math because we're smart, okay? And we know that the material is copper for both of them, so the density is going to be the same. But you will need to do this when you have different materials. So now you know the method, in case you get a question that has objects of different materials. Okay, let's see the next one. Four objects are situated in places with different gravitational field strengths. Which object? We did this question. I'm going to skip this. Four rocks. This is the same question. I'm going to skip this as well. It's just rearranging W equals mg to find G for each of them. And whichever has the highest value of G is the right option. A stone has a mass of 390 grams and a density of 2.7 grams per cm cube. Cooking oil has a density of 0.9 grams per cm cube. Which mass of oil has the same volume as the stone? Okay, so first of all, look at the key terms in the question. The question's asking you the mass of oil that has the same volume as the stone. So you're given the important information for the stone. You have the mass of stone and you have the density of stone. So first step is to find the volume of the stone. So mass over volume, and we'll rearrange this formula for volume, and you'll get mass over density. And how did we get that? We just like took V to the other side and took rho to the other side. Okay? Now, mass is 390, well, density is 2.7, and that is 144.44. So this is cm cubed. Please don't forget the units. This is the volume of the stone. So I can say V sub S is equal to, wait, 144.44 cm cubed. Now, you want to find the mass that will give you the same density as the stone. So you'll test every single option. Let's start with part A. You have the mass and you have the density. And you found the volume here, okay? So you want rho is equals to mass by volume. You'll rearrange for mass. And that is rho, sorry, no, yes. This rho is just the name of the symbol that I'm using here for density. So rho V, your density is 0.9, and the volume is 144.44. That is going to be 0.9, 130. So yes, part A, fortunately, is correct. We didn't have to test all of them. I mean, we don't need to. You just find the volume of the stone and you plug it into your formula and you'll get the mass that you need for the oil to be. A scientist places a rock on a spring balance. She then places the same rock on a beam balance. At the North Pole, the gravitational field strength is greater than that at the equator. She performs the experiment at the North Pole and the equator. How do the readings at the North Pole compare with those at the equator? So before you do this, you want to know what each of the instruments is measuring. Okay? So the spring balance is measuring weight, and the beam balance is measuring mass. Just go back to the notes and see which one of these is the same. Mass is same everywhere, so it's going to be the same at the North Pole, but weight's different, so mass is needed on beam balance. Sorry, I think I chose the wrong option. So masses needed on beam balance are going to be the same, and the scale reading on the spring balance is going to be different, so part B is the right one.